In this lesson, we will take a closer look at TDMS files and binary files. These are three common file types that you might work with in LabVIEW: text files, TDMS files, and binary files. Text files are the easiest format to use and share, as many applications, such as Notepad and Microsoft Excel, can read from or write to a text file. Data is represented as strings in text files. TDMS is a binary file format created by National Instruments that is optimized for saving measurement data to file. You can use TDMS files to organize data and store information about your data. You can use TDMS files to write and read data at high speeds. You can also use an add-in to view TDMS files in Microsoft Excel. Binary is a file format that you can use when you want to write to or read from a binary file with a specific binary format. The TDMS file format is a binary format. Explore this table to compare text, binary, and TDMS files. The TDMS file format is a binary format that was designed specifically for saving measurement data to file. It contains two types of data: raw data and metadata. You can use the TDMS file format to store measurement data, along with channel-specific properties such as channel name, measurement units, test limits, and sensor information. The TDMS index file is a binary file that provides consolidated information on all the attributes and pointers in the TDMS file. This speeds up access to data. The TDMS index file automatically regenerates if it is lost. The TDMS file format is structured using three levels: file, channel group, and channel. A single TDMS file can contain multiple channel groups, and each channel group can contain multiple channels. So you can choose how to organize your data to make it easier to understand. For example, you may have one group for your raw data and another group for your filtered data in a single file. Or you might have multiple groups that correspond to sensor types or locations. Additionally, at each level, you can store multiple properties to provide metadata. This helps you achieve well-documented and search-ready data files. Use the TDMS functions to write to, read from, and search TDMS files. First, let's explore how to write to a TDMS file by looking at the TDMS Logger VI. This project is found in the Exercises, Demonstrations, TDMS Logger and Reader folder, so you can follow along. We begin by using the TDMS Open function. Then we set TDMS properties using the TDMS Set Properties function. To set a property at the file level, leave the group name and channel name inputs unwired. Then specify the property name, which is a string data type, and then set the property value, which can be any data type. Here, we set an author property to the value provided by the operator string control. And here, we set a timestamp property to the output of the getDateTimeInSeconds function, which is a timestamp data type. Next, we write multiple channels of data to the TDMS file. The multi-channel data is passed as a 1D array of waveform data. We use the TDMS write to create a name for every channel and create an acquired data channel group for these channels. Then, we use the TDMS set properties to set a property at the channel group level by wiring the group name input. This example creates a sensor type property for the acquired data channel group and sets this property value to simulated. Next, we filter the acquired data using a cutoff frequency, and we write the filtered data using the TDMS write function. We also create a name for every channel and create a filtered data channel group for these channels. Then, we use the TDMS set properties to create a cutoff frequency property for the filtered data channel group and set this property value to the lower frequency dBL value extracted from IIR filter specifications cluster. Lastly, we use the TDMS function to close the file and then check for errors. Now I will run this VI, choose a location for the TDMS file, and now the TDMS file has been created here. Now let's explore how to read data from a TDMS file by looking at the TDMS Reader VI. We begin with the TDMS open function. Then we can get TDMS property values using the TDMS getProperties function. To get a property at the file level, leave the group name and channel name inputs unwired. Then specify the property name and the data type of the property value. For example, the author property value is a string, so I've wired a string data type into the data type input. The actual value of this constant does not matter, only its data type matters. After wiring the data type input, the property value output adapts to match the data type of the data type input. For the timestamp property, I've wired in a timestamp data type, so my property value output here now also has a timestamp data type. Next, we read data using the TDMS read function. You can use the group name and channel name inputs to look for a specific channel group and/or channel. You can also leave both inputs unwired to return all data in the TDMS file. In this case, the TDMS read will return all the channels in the channel group specified by the channel group control. Next, we will use the TDMS getProperties to get properties at the specified channel group level. If we leave the property name input unwired, we can return all property names and values for the specified channel group using the property names and property values outputs, which will be arrays. Now I will choose the acquired data channel group and run this VI. The TDMS functions have returned file level properties here, the acquired data channel group data here, and the acquired data channel group property names and values here. As you can see, the data has a lot of noise. Now I will choose the filtered data channel group and run the VI again. Now you can see the filtered data as well as the corresponding cutoff frequency of the filter. In this example, the writer VI passes a 1D double precision array containing 100 values to the write to binary file function. Each DBL is 8 bytes. The binary file created by the writer VI will contain 800 bytes because there are 100 DBLs and each DBL is 8 bytes. To read a binary file correctly, the reader must know exactly how the binary file organizes its data. Because we know that this binary file contains multiple DBLs next to each other, this VI uses the get file size to get the file size in bytes. In this case, the file is 800 bytes. And then divides the total number of bytes by the size of the DBL data type, which is 8 bytes, to get the total number of DBL numbers in this file. Then, the read from binary file function is configured to interpret the read data as a DBL, and is configured to read 100 DBLs from the file. Compared to other formats, binary files are complex to work with and require an intimate knowledge of the file format. You should evaluate using text and TDMS files before considering using binary files. You've completed this module. Here is a summary of what you've learned.